So Theo, are you able to share your slides?
Sure.
Great. Yeah, so I'm really glad to welcome Theo today. I guess I know Theo via the Julia programming language community. We both do Gaussian process related stuff in Julia, and we know each other that way. Theo's a PhD student at Technical University of Berlin, working with Manfred Oppert. And today he's going to talk about automated augmented conjugate inference for GPs. Take it away, Theo.
Okay, thanks a lot. So I'm very happy to be able to give a talk to you today. We don't get this many opportunities in these difficult times. I'm a final year PhD student at TU Berlin with Manfred Oppert, that you might know from his GP contributions. And what I'm going to present today is basically kind of a generalization of some work that has been happening during my thesis, mostly with Florian Wenzel, and of course my PI, Professor Oppert. So I would like to start with a very general motivation, which is the motivation for good representations of your models. I'm actually going to start by talking about another paper which I have nothing to do with, which is this automatic reparameterization of probabilistic programs by Gorinova, Moore, and Hoffman, given in ICML last year. And what they say is, well, they just actually take this very well-known fact that you have centered and non-centered representation. So these graphical models are quite different, but the models they represent are exactly the same. So in one case, we define our prior very specifically, so theta is a prior of mu, which can goes to y. In the other case, we actually directly use theta and mu on y. And if you integrate things out, or if you compute means, you're going to get the same thing. However, when you look at the posterior of these different variables, they're very different. So if you look at the Niels funnel, the centered representation gives this horrible example that everybody tried to bash his head against to see if its algorithm is the best of all. But if you actually use an uncentered one, it's a nice, beautiful Gaussian that is so harmless. And it's just to point out that they did not, I mean, the paper is about more. You can find some kind of manipulation between the two, but this is not the point. The point is representation matters, and you can simplify your problems infinitely by finding the right representation. So why do I speak about this? Is, well, I was told that you know about Gaussian processes, so I will not go about them. And I think you also know about Bayesian inference. So when you have a Gaussian process with a Gaussian likelihood, you know the posterior analytically, everything is beautiful as long as you don't have too much data points, but that's another story. Everything works very smoothly. Now the problem is, what if you have other likelihoods? So for non-conjugate likelihoods, which is literally anything but the Gaussian, for example, the student-T, Laplace likelihood, if you want a classification with a Bernoulli likelihood, well, there is no analytical solution, and that's how it is. So what people do usually is that you do some approximate methods like variation inference. You can sample, of course. But the problem is all this method is you need sometimes gradients that can be unstable, that can be very slow. A lot of difficulties arise. So what I want to propose is a new representation to solve all this problem. So here's a plan. We start with a nice and simple GP model. We have some data X, and we want to make, which have some output Y, and F is passed to Y through a certain likelihood, which is non-conjugate. The conjugate case is of course trivial. So what we do is we construct what we call conjugate augmentation, where we transform our likelihood with a new variable omega such that this becomes conjugate. And I'm going to come back to this later. So what do we want this? Well, if you do this, and I'm going to show it's possible, of course, you automatically get full conditionals in analytic forms. And of course, it's something you want, because then you can have some very efficient inference algorithms like Git Sampling. That's the most obvious one, but also variational inference with coordinate ascent updates. So you can just converged in a few steps this way. So this is not a new approach. There have been quite some papers in the last years about this. For example, if you have a logistic transformation on your GP, you can use polyagma variables as augmentation. This was developed by Paulson and Scott. There's something called the Bayesian SVM likelihood, which is also augmentable. This was first developed by Lindemann, and we expanded it to GPs. And you can even go further. We actually, 2 years ago, developed a paper which worked with multi-class classification. And you actually start with some kind of softmax, and you end up with a fully conditionally conjugate model at the end. So everything is Gaussian at the end, although you start with something different. And if you want, at the end, I have like this bonus slides to see how it works. But let's see if there is time. So what's the secret? The secret, at least one of them, there's many options for these augmentations, is scaled mixture of Gaussians. So what are scaled mixture of Gaussians? You know what we call typically mixture of Gaussians, where we have multiple Gaussians with different means, and we attribute them some weight. Here we do the same, except that we have an infinite mixture because we go over the real numbers, the positive real numbers, and we change the variance and not the mean. And of course, we actually attribute a certain prior to this variance. And so if we integrated out this mixture, we would actually get our likelihood. And this is, for instance, the case for the student distribution. This is pretty well known in the statistics community that student T is just a Gaussian with a prior on the variance, actually an inverse gamma prior on the variance. And if we were to integrate out the prior, we would automatically get the student T. Now, as I said, the big interest about this augmentation is that, about this representation is that we can augment our model. So how does this work? So we start with our initial model that I showed earlier. And how do we get rid of this integral? Let's say we know that P of y given f can be rewritten as this scale mixture. We just remove the integral by just adding omega to our model. So this means that technically we should have more cost, but we're going to see that it's actually worth it in the end. And in this context, we actually get the full conditionals in closed form automatically. And that's what, again, what I'm going to show later. So yeah, we can do Git sampling. We can do variational inference in a few steps. That's just a Bly approach, like David Bly's in his paper about variational inference explains that we can find the optimal distribution directly by taking the expectation, the exponential of expectation of the log of the full conditionals. So since we know now the full conditional is closed form, we can actually compute the expectation and get the thing. And since we need to go over f and omega, we have this CAVI, so Coordinate Ascent VI variational inference updates, which allows us to converge to the maximum, to the optimum in 2-3 iterations. So we get exponential convergence and a lot of beautiful other things. So now here's a big question. This is all in theory, right? So the likelihood can be written as a scale mixture, and if it can, we can do all this stuff. But the problem which was not solved yet is that how do we find it? And the answer, or at least one of the answers to this, is a Schoenberg theorem, which say that for phi, a positive definite radial function, we can rewrite it as a scale mixture of Gaussian. So here I didn't write the Gaussian itself, but just the exponential of minus x squared. And you might notice this is quite similar to what we would do with kernels. So in kernel, you would have the Mercer theorem, which tells you that you can do a Fourier transform. Here, what we do is actually a Laplace transform or LTS integral. So what means to be positive definite radial? It means that phi of x, for all x positive, phi of x is always positive. The derivative of phi of x is always negative. The second derivative is always positive, and etc. So it also means that phi should be differentiable. It should be C infinity, so always differentiable. And what does it mean in practice? Like what kind of functions are corresponding to this? What kind of functions are positive definite radial? It's mostly this super Gaussian type of functions. So functions which are more peaked than the Gaussian, but tends to have also a heavier tail. And the Gaussian is itself, of course, positive definite radial, because if you just take P being the delta Dirac function, you just get the Gaussian. Okay, now we know that functions which match this definition can be used. And I'm going to give you some examples about which function can do this. But the problem is that we still don't know how we can find P of omega. And we're going to need P of omega because that's our new variable and we need to know everything about it. So you might notice that, and I actually told that this is a Laplace transform. So the Laplace transform is like the Fourier, but in real space. And it's also, and this is going to be important later, is just a negated moment genetic function of P of omega. Moment generating function are absolutely amazing tools as our cumulant generating function, and we're gonna use that later. So the simple answer is, well, P of omega is just the inverse Laplace transform of phi. By applying the inverse Laplace transform, we get the Laplace transform. Applying the inverse Laplace on the Laplace, you get the original function. And from this definition, and this definition can actually be used sometimes. Sometimes you just apply inverse Laplace transform, you pass it through Mathematica, Wolfram Alpha, and you get an answer. Sometimes not, but it's also possible to solve this problem. We can already define a general family of distribution. So I'm going to call it a pi of phi because it's implicitly depending on phi. And I'm just going to add this additional parameter c, which is just an exponential shift, which means that we move the distribution on the Laplace space. And this is going to be useful to define conditional distribution in terms of other parameters. And again, what does this distribution look like? Mostly like a generalized inverse Gaussian. So the generalized inverse Gaussian is a super general distribution, which has basically all specific cases or known distribution like inverse gamma, inverse Gaussian, gamma, exponential, all this distribution defined on 0 to infinity, they kind of fit here. Okay, so now we know how we can do this. And to make things a bit simpler, so the idea that you should not have to derive all this by yourself, we define the general scheme. So assuming that your likelihood can be written this way. So we have a constant, which might depend on hyperparameters. We have this exponential term with g of y times f. This is just a linear term. And since it's a linear term, once we're going to transform phi into something else, we're still going to keep our Gaussianity because we just apply a linear transformation on our Gaussian. So this is still Gaussian. And phi is our positive definite radial function. And now what is h? What I defined inside? Well, it should just be some kind of quadratic function. So some alpha of y minus beta of yf plus f squared. So something which is just Gaussian. And I kept the color here because I'm going to now show a few examples and we can match the color to what element is what. So for example, let's take student T that I talked about earlier. So we have this C of nu, which is just this gamma nu plus 1 over gamma nu, I think. And then we have phi, which is the 1 plus x over nu to the power of minus nu plus 1 over 2. And then we just know alpha is y squared, beta is 2y, and f and gamma is 1. And if I just pass phi to my inverse Laplace transform, and I make sure to use the square root, important, well, my P of omega, Wolfram alpha would directly spit out P of omega is just inverse gamma with these two parameters. And we can verify this. If I sample from P of omega and define a Gaussian every time, and I just basically make a Monte Carlo integration of the function, I recover exactly the student T distribution. So the approximation is a dashed line, and the true one is the blue line. And all the rainbow colors you see are all the samples. Now we can do the same with logistic. So why do I choose logistic as well? Because in the logistic function is just defined by this 1 over, usually we write is 1 over 1 plus exponential minus yf, except that it's not so clear what is there here. But if you write it in a different way, we have now this exponential term, the blue one. We have our phi, which is cos h of 0.5 square root of f squared. And yeah, so now what if I pass this to Mathematica? Mathematica will tell me I have no idea. But what Paulson and Scott told us is that this is a polar gamma distribution, which basically corresponds to an infinite mixture of gamma distribution with certain parameters. And this is not really helpful. But what we're going to see is that by having a marginal setting, we can actually recover all what they found, but in a very specific framework. And again, I can do the same thing here. So now we see that it's not always centered in 0 because we have this exponential shift, but we actually recover the logistic function again. And I thought one can also get creative, right? Because this positive differentiable function feels very familiar with kernels, especially stationary kernels. And I thought, okay, let's take the matter free half kernel and let's define the likelihood of it. All you need is normalization constant, right? And if you do this, well, you can do this first, and you get this specific phi function. And once you pass it to Mathematica, you actually get an exact transformation, which is just this inverse gamma distribution. And again, we can try it. And of course, this is valid for matter in 5/2, 7/2, whatever. Since it's always fulfill the condition that it's positive definite radial, this is going to work. Okay, so let's pick on how we can use this. So variational inference, I don't think I need to spend too much time on this either. I guess you're all pretty familiar. We look for the optimal, we take a familiar distribution and we look for the optimal parameters, which minimizes the KL divergence between the true, posterior, and our distributions. In this case, we use the mean field approximation. So we assume that all the omegas, so we need 1 omega per data point, is independent from each other, and they are themselves independent from our GP. This assumption is actually, well, it sounds strong, but it's not that much in practice, as we're going to see through the difference of elbow that we get. But this is literally the only difference we have from the original model. Because if we actually were able to compute Q of f omega without the mean fields, we could always integrate out omega and recover the exact f. And this is even more clear for Gibbs sampling, and I'm going to talk about it later. So using the framework of Bly and al, we just can compute the optimal distribution of f and omega I, given some expectation. But what expectations do we need? So we need the expectation of f, f squared, and omega I. Well, the expectation of f and f squared, that's pretty straightforward. Even very, very straightforward, because we know how to do this. With these Gaussians, everything is beautiful. Now, what about omega? If we still stick to the general case, omega is this inverse Laplace transform of some function. How do we compute an expectation of this? Well, that's where the moment derivative function actually comes into place, because the expectation of omega is just the derivative of the moment derivative function at t equals 0. Cool, right? So I just put in my Laplace transform of q of omega, and this is just corresponding to phi. So I just need to derive phi for, and what I get in the end is minus phi prime over c squared, because c squared is these variational parameters that I talked about earlier, over phi. So you just use your favorite AD transformation, AD software, and you get your moment. And this is actually true for any moment. So you could actually compute the expectation of omega squared by taking the second derivative, etc., etc. And this is possible because we know that phi is infinitely differentiable. So here's like a small showcase for a few of the likelihood I talked about to show how fast this actually converges. So here you have 1, 2, 3, like you see in 3 iterations, it already converged to the optimum. Well, with gradient descent, which would be like the, let's say the Hensman approach, would take much longer. And especially for Bernoulli, you would actually get worse results. As I said, we do this approximation, right? So we looked at the elbow, the difference between the true model, the original model, and the augmented model. And you indeed see a difference between the elbow. So the elbow of the original model is always going to be some kind of lower bound on the augmented model. But when you actually look at the error, well, the model basically performs the same. So there's no difference in this terms. Yeah, and a quick note is that this approach, which is done at least in the logistic case, was also developed completely independently by Iacola and Jordan as an optimization thing. They actually just consider Taylor expansion and get the same kind of results, but they have absolutely no probabilistic perspective on the topic. If we now take our augmented model and scale it, so we use stochastic versional gradient descent, stochastic versional sparse versional Gaussian processes, and we use stochastic versional inference. And we can do this by, instead of CAVI, we have some convex updates. So we just add the previous parameter with a partial of the update. So we know that we're always in the right domain. Again, we get some huge speed up and conversions in few iterations compared to other standard methods. Now, the thing that I actually find the coolest is not the versional inference, but the Git sampling. So one important difference is that although we have an augmented model and we're gonna alternate between sampling omega and f, we're actually gonna still recover the exact model because what we're interested in the end is f. And by just taking f, what we do is that we marginalize out all the omegas, which means that we recover the original model. So obviously you have this n square, n cubic cost per step, but you get the exact thing. And I kind of skipped an important thing. Is like I said, like, yeah, we just do Gibbs sampling, yeah. But how do we actually sample omega? Well, this can be easy and this can be hard. There's an easy way, which is your Wolfram alpha just got you a very nice distribution you can sample from, probably a generalized inverse Gaussian, which are actually not so easy to sample from. But this is another topic. The other way is to use another statistical fact using Laplace transform and distributions, is that the cumulant distribution function, big F of omega here, is just the inverse Laplace of the Laplace divided by S. And again, we know that the Laplace of P is just phi. So we just need to compute the inverse Laplace, but it's a bit easier said than done. We can use naive sampling. So we sample from U, and we just need to solve the inverse problem of finding omega as f minus 1 of U. This sounds hard, but this is possible. And there are very efficient techniques, such as this paper by Readout, where we make approximation of the inverse Laplace transform, and we do a Newton step to converge very quickly to the correct value. And we can even use a previous value to find even more quickly the omega. But that's where the experiments shine. Here I'm just showing the lag, so the autocorrelation plots for different likelihoods on some standard data set from UCI, I suppose. And I'm comparing the, well, very stupid approach of just sampling from Metropolis Hastings with having a Gaussian proposal, comparing this HMC with optimized parameters, and finally our approach with Gibbs sampling. And what you can see, I think, directly is that the correlation goes drastically to 0 after just 2 samples. So we don't even need thinning. I did not speak about the burning, but this is also the same thing. It converges. You almost don't need burning because it will directly converge to the right stationary distribution. So this works really well, even. So yeah, just to summarize, we start with the likelihood, and we actually start to consider it as a different representation by using an augmented variable, and we saw how we can do this in an automatic way. We can find the full conditionals given this new augmented model. and then we can apply our favorite inference schemes. So yeah, by just augmented our model with new things, we made the inference easier and much faster. And also, I think I cannot emphasize this enough because I've been doing all the code in the experiments. It's so much more stable. I've been using dbFlow and other tools, and they always sometimes struggle or they just pop out. And this is always so robust and always converging to the right thing. This work is not restricting to Gaussian processes because all I wanted from the start was to have a Gaussian likelihood. So if I have a Gaussian prior, this is also conjugate or conditionally conjugate in this work as well. And I mean, we're working on a journal paper for now, which should introduce this concept as well of making some kind of Gaussian bridge, where you not only augment the likelihood, but you also augment the prior. So you start to have two augmentation variables, but then you have your Gaussian prior and your Gaussian likelihood, so you can connect them and get everything you want done. I have a quick proof of concept. I was using some kind of studentive processes, but not really, and this works pretty well. And well, the problem is that one question that you will probably ask is, well, it sounds pretty limited, right? These positive definite radial functions sounds like a very restricted class of functions. And it's true. But there's actually more possibilities. And again, this is something we're working on this journal paper. And I can talk about it in this bonus slides I have on how we did it for the softmax function. But this is possible. Like the general idea is to find some kind of moment generating function somewhere. Again, representation matters. And of course, I'm part of the Julia community, so I have to advertise for Julia packages. So I have my own augmented Gaussian processes package, where you can even, by doing some pattern matching yourself, I did not manage to do this automatically yet, you can give every element of your function, so this alpha, beta, gamma, etc., through a macro, and this will automatically create a type here, for example, aug Laplace, and you can pass it to my models, and everything is gonna run so smoothly with them. And I'm lying because I've been holding this project back for a few months, and I was like, oh, I need to present this, and so I started to do PR yesterday, and things are working almost, but they will work very soon. Okay, thanks for your attention. And yeah, as I said, I have more things which involves cool plots and animations, but this is maybe a bit over time. I don't know what to say, Will.
No, great. Thank you very much, Théo. Yeah, thanks for the talk. Before I ask any questions, does anyone have? Oh, he's clapping. So I thought you had your hand up already. Does anyone have any questions? Okay, I'll kick us off. So you mentioned earlier in the talk that the mean field assumption with VI was kind of all you could do. I was wondering if you could kind of dig into that a little bit more, because it, like, for example, I kind of thought when reading your paper, like, oh, well, could you do like some kind of structured VI thing here? And is the answer no?
So the problem is that if you start to, if you don't use main field VI, right, you have the problem of how do you compute the expectations? And this is really not so clear, right? Because now we were able to compute the expectation of given omegas because we know we can use a moment generating function. But if you have f omega, it's not so clear. In sampling, it's much easier because you can always assume that your posterior is the right thing. But for variation inference, it's not so straightforward. Actually, yeah, for this other model, which is in this other slides for the multi-class, we actually had this like, it's actually 5 augmentations in a row, basically. Which is why I find it fun. If you're into mathematics, it's like mind blown after mind blown. And
do you want to just take us through that quickly?
Yeah, sure. And there's actually just to why, like, there's actually 2 augmented variables which you need to consider together. If you don't, it doesn't even work. So I think it flows from the model. So yeah, I mean, I can quickly go through it. There's also colors and cool moves for making it understandable. So this is paper which was published in UAI. So the idea is like you want to do multi-class classification. So you have like, let's say here we have 3 classes, they're optimized, and we want to merge them. So the well-known likelihood used, categorical of course, but the link you use would be softmax. Most people would use softmax. There is multinomial. You can also use multinomial and other stuff, but let's stick with softmax. Actually, let's not stick with softmax because softmax is very hard to work with. What we do is working with a modified version of softmax, which is you replace the exponential by sigma, which is a sigmoid function. And the obvious thing which is going to end up is we're going to use polygamma in the end. So here's the steps. And that's where we use completely different augmentations here, which are not related at all with what I explained so far. That's why I'm saying this is not limited. First thing, analysis 101, 1 over x is equal to this integral. So again, kind of like, this lambda looks nice. I don't like integrals. So I can just put my sum inside, right? And I remove the integral by just adding lambda as a new augmented variable. So it should also appear in my graphical model. Okay, now because it's an exponential, I can transform the sum as a product, which is the whole point of the thing, getting rid of the sum. And now, second thing, and that's why we cannot use exponential, the softmax, traditional softmax. Sigma of x is symmetric around 1 minus. So if you take sigma of x is just equal to 1 minus sigma of minus x. And we just change it, right? And that's where, well, you need to be Professor Oper to notice, but this is just a moment genetic function of a Poisson distribution. So, well, we just replace it, right? So now I just replaced my exponential by a sum, infinite sum, but I don't like a sum. So I just say, well, now n is n new nk I introduced, which is my Poisson variable. It's just part of my model. Okay, so far so good. I have something which looks a bit nicer now. And now I can finally use my polygamma thing, which looks like this. This is just something similar. Now this is what's similar to what I showed you before, because if cos h is positive definite radial, cos h to the power of n is also positive definite radial. I get this crazy thing. I don't like integrals. And now I actually get something which is a Gaussian distribution. And now it's conditionally conjugate. I get this crazy model, right? And full advertisement. This model is terrible. It works much, much worse than softmax. It has better uncertainties calibration, but that's it. But I think it's mathematically very elegant, and it opens a way of like thinking about how you can transform the model in different ways. Especially this moment genetic function approach is, I think, extremely powerful to find stuff. And this is kind of similar to what we did, but we took the long way of saying moment genetic function or Laplace transformed, therefore it works. That's the same idea. Yeah, that's it.
Cool. Yeah.
It was just to show you like a bigger scope about what augmentations can be.
Yeah, yeah.